Welcome everyone. So this is our April session from the machine learning seminar, and I'm Katerina, organizer of this seminar. And next to me is Pat, my colleague. She will introduce our guest speaker, Geoff from Monash University. Please, Pat.
So this is Geoff Webb, and he's from Monash University. And I could read this, but I'm not going to. He's been doing machine learning a long time, pretty much as long as me. I knew him first when I was at Boeing, which was a very long time ago before I came here. But what he's going to be talking about today is basically time series classification, which I don't know a lot about. So that will be interesting. So take it away.
Thanks very much, Pat. Thank you very much. Oh, screen sharing's been disabled, so it's going to be a very boring talking head only if somebody doesn't enable it.
We'll try to do that, right? So I apologize. So.
No. Right click on it, that's it.
Yep.
More.
Yeah. Co-host?
Yes.
Okay. And now you should be able to do.
Lovely.
Awesome.
Excellent. It would be hard to talk just waving your hands. I would find that very difficult.
Great. Can you see my screen?
We can.
Excellent. So it's supposed to be a video, but it's not videoing, but we'll put up with that. So thank you very much for inviting me to talk to you this evening. Very great honour, and I'm very excited by the research that my group has been doing, and delighted to have the opportunity to share it with you. And hopefully Pat will know a little bit more about time series classification by the time I've finished. If not, I will have failed fairly badly. It's going to, now it moves. So the world is dynamic, in a constant state of flux, but most machine learning systems treat it as if it were static. They take a snapshot of data at a particular point in time and learn a model from it, and then apply that model. One data type that captures dynamics is time series. So you'll all be familiar with stock markets time series, but they are increasingly ubiquitous. So sensors on everything from machines to wearable devices, sound is a form of time series, and the list goes on. The time series classification task is to take a set of series for which you have labels, so they are in two or more categories, and to work out how to take the raw series and from that determine what the label should be. My group's interest in the time series classification problem has been largely driven by the use of Earth observation to monitor environmental variables, such as land use. So being able to determine for each pixel in a satellite image what is being grown there, for example. Now, it turns out that you cannot readily distinguish, say, corn from soybean by what you observe in pixels for each at any one point in time. Rather, you need to look at how they evolve over time. So what is displayed here is for each, right? So each of these lines represents the evolution of a single pixel in an image. Each of these lines are corn pixels, each of these lines are soybean pixels, each of these are wheat pixels, and each of these are broadleaf tree pixels. So you can see that corn shares an overall similar shape, soybean shares an overall similar shape, etc. Now, one of the fascinating things about time series classification is that there are hugely differing aspects of a series that may potentially be relevant to classification. So to take a couple of examples from ECG, so monitoring a person's heart, if you want to determine whether somebody's heart is racing or they have a normal pulse, then it's the frequency of the signal that is relevant. If you want to work out whether their heartbeat is irregular as opposed to regular, then it's the variance in the frequency that matters. If you want to work out whether their pulse is strong or weak, then it's the amplitude. And while I'm not an expert in such things, it's quite credible that it may be possible to identify particular types of faults in the heart by the shape of, say, the peak of each beat in the heartbeat. Right, so local patterns may be important. And as we saw with the satellite image analysis, the global pattern may also be very important. I should beg forgiveness for my dog who's in the background giving a bit of commentary. I hope that's not too disturbing for you. Now, I'm going to be doing a lot of talking about comparisons between multiple approaches to doing time series analysis. And to do that, I'm going to use critical difference diagrams. So I'm going to now give you a brief introduction to critical difference diagrams, either as a reminder or to let you know what they are in case it's not front of mind. So often in computer science, we have many different ways of doing something which we can apply across many different tasks, and we want to have some easy way of getting an overview of the relative performance of those multiple approaches across multiple tasks. The critical difference diagrams were popularized by Demsar in 2006 in a very highly cited and much used paper. And he gives us an example, the task that I hope you can see, the table that my cursor is moving over, where we have 4 variants of the famous machine learning algorithm C4.5. So C4.5, C4.5 plus M, C4.5 plus CF, and C4.5 plus M plus CF. And we have around a dozen tasks which we're going to use to compare them. And what we're interested in is getting an idea of whether these variants of C4.5 lead to higher accuracy. So for each task, for each algorithm, we have an accuracy. What we do then is we rank those accuracies. So the highest accuracy on the adult task is C4.5 plus M plus CF, so 0.798, higher than the others, so it gets rank 1, and so on down to C4.5, which has the lowest rank. For the next one, C4.5 has the best rank, and so forth. Then we can take the average of all those ranks. So we see C4.5 over this dozen or so tasks has an average rank of 3.1 something. C4.5 plus N has an average rank of 2, plus CF has 2.89, and plus M plus CF has 1.96. We then plot these on this critical difference diagram. The lines next to each algorithm come to the rank, so we get a pictorial depiction of where they lie on the possible line of ranks. And then through a bit of statistical magic, Friedman rank test, we compare the performance and are able to work out what critical difference is statistically significantly different. And we can then draw a bar to group together those algorithms whose ranks are not statistically significantly different to one another. So what this graph is telling us is that over these tasks, comparing using accuracy as the measure, you cannot statistically significantly distinguish C4.5 from C4.5 plus CF, or the 3 variants of C4.5, but that these 2 variants of C4.5 are statistically significantly superior to C4.5. Well, sorry, that's a fairly laborious explanation, but I'm going to be using this a lot, so important that you understand it. Okay, so this now gives me the tool by which I can explain this next diagram. So because there are many things which may be relevant to time series classification, there's been much work on developing many different forms of classifier, each of which can pick up on these different things. There have been a large number of specialized time series classifiers, and there's been a benchmark repository of classification tasks, so the University of California Riverside repository. And until recently, there was no one time series classifier that dominated on that repository over all of the alternatives. And then there was a revolution. So the revolution was the introduction of ensemble techniques. So many of you will be familiar with the idea of ensemble techniques. Instead of using a single classifier, you take many classifiers, apply them all to your task, and then in some way combine their multiple predictions to produce a single prediction. So one of the first of these was the elastic ensemble, which combines many nearest neighbor classifiers, where each of the nearest neighbor classifiers uses a different similarity measure, specially designed to pick up different aspects of similarity between different time series. And you can see here that the elastic ensemble is significantly more accurate than any of the nearest neighbor classifiers that it comprises. So it is an ensemble of all of these classifiers. And they didn't stop with just an ensemble of nearest neighbor classifiers. All of these time series classifiers up the right-hand side are ensemble techniques. So shapelet transform uses many classifiers that pick up on localized shapes. So a shapelet is a small shape, as in my example of how maybe the shape of the top of a heartbeat may tell you something, and so forth. And then the COAT classifier started putting together these ensembles. So COAT is an ensemble of ensembles. Flat COAT just took all the ensembles and took a majority vote. Then Hive COAT took the ensembles and did a weighted average. So we can see ensembles and then ensembles of ensembles. Really, to put not too fine a point on it, wiped the floor with everything which had been done previously if you are talking about a generic classifier. So they showed that it was possible to be much more accurate than the previous specialized classifiers, but they simply didn't scale. So for one of our satellite image classification tasks, where we had 1 million examples, that's a very small Earth observation task to do the entire Earth's surface with the particular satellite that this one is drawn from is 1.5 trillion examples, so many orders of magnitude greater than this. But Hivecode applied to this problem took 8 days for 1,500 time series, and we estimated it would take over 200 years to learn from all 1 million examples. So clearly it wasn't going to be useful for our Earth observation task. So we set ourselves the task of trying to create much more scalable time series classifiers that we hoped would be almost as accurate as this incredibly accurate but not remotely scalable approach. And I've been extremely pleased with what we've achieved. I'm going to take you through the 3 types of approach that we've pursued. So first of all, tree-based approaches. So decision trees are a classic approach to scalable classification. Then deep learning, because deep learning seems to be good at almost everything. So we thought that we should see how it performs here. And then finally, the rocket system, which I will explain when we get there. This is very recent work. I'm going to present work from 4 papers published in the Data Mining and Knowledge Discovery journal, 1 in 2019 and 3 of them last year. And then the most recent rocket work has just been accepted for publication in this year's KDD conference. So let's start with the tree-based classifiers. And this is the PhD work of Ben Lucas. So we started by thinking just about how we might take the elastic ensemble, so that's the ensemble of many nearest neighbor classifiers, each using different distance measures. How might we take that and create a scalable version of that? And we thought, well, one possible approach would be to use divide and conquer. So it's a standard computer science approach to scaling things up. So split the overall problem into sub-problems until you get to something very simple and then pass the cumulative result back up. And in our work, we've chosen, wherever there are design choices, if possible, use the same design choices was used in Elastic Ensemble. And the reason for doing this isn't because we think Elastic Ensemble had particularly good design choices, but more because we want to make it clear that the differences between the performance of our approach and Elastic Ensemble is due to the fundamental difference in strategy rather than because we made a better choice about one of the parameters, one of the distance measures. So the divide and conquer approach used in machine learning is decision trees, but standard tree-based splits don't work for time series, right? So a standard way to do it would be to treat the time series as simply a set of attribute values and then choose one time point and split on the values at that time point. But that's has been tried, but it's not a very successful approach. So what we hit upon was instead to use proximity. So this uses the concept of neighborliness, which comes from the nearest neighbor classifier. So we have 11 different distance measures used in the elastic ensemble, and we're going to use those to calculate how like an exemplar an object is. For each branch going from a node, we're going to choose an exemplar. So here we're looking at a binary split. And we then apply a distance measure to work out how each of the series at the node, how close it is to each of the exemplars, and send it down the branch corresponding to that exemplar. So we can see here if we have two classes where one has a peak and the other doesn't, this simple method can very readily split the two up. You can see that as projecting the time series onto a multi-dimensional space defined by distance or similarity to each of the exemplars, and then choosing a simple hyperplane to separate them. So in detail, use decision trees, but replacing conventional decision tree splits with similarity comparisons. We're not just going to use any old similarity comparison. We'll use the 11 specialized time series similarity measures, which have been developed over a long time of research into time series analysis. Each branch is going to have an exemplar. We'll choose one exemplar per class, and so hence have one branch per class. So each branch has an exemplar. Each node or each split has both a measure, so one of the 11 measures, and a parameterization of that measure, because many of the measures have parameters. And then for classification, we simply pass the series down the branch whose exemplar it is most similar until we get to a leaf, and the leaves then have associated classes. Now, this leaves us the problem of how do we choose the exemplars, how do we choose the distance measures, and how do we choose the parameterizations of those distance measures? And our choice is to do all of that at random. Why do it at random? Well, first of all, it's fast, and one of the things we want to do is to be fast. Another reason is because random choices have low bias. So just to remind you about bias and variance, if you're not familiar with the concepts, you can think of the bias and variance of a classifier as being similar to what happens with an archer when they're hitting it, shooting at a target. Right, so an extremely precise archer will always be on target. Another type of archer might be might have a good central tendency, right? So they are aiming towards the center of the target, but they're not all that accurate. So there's a considerable spread. Another possibility is that you're very consistent, but consistently off target. Another possibility is that you're both consistently off target and have considerable spread. So you can see that, if you move this to the classification task, so being on target equates to selecting the correct task. That being having spread relates to variance, so you tend to be on target, but as you try time and again, sometimes you move away from the target. High bias is being consistently off target, and high bias and variance is both being off target and having a spread. So you can see that to be accurate, you have to have both low bias and low variance. And what ensembling tends to, and what random choices do is reduce the bias, but they tend to introduce high variance. So you tend to get something looking like this. And then ensembling tends to reduce the variance, taking us back to the low bias, low variance position. And now the major training time, because all the choices we want to make are at random and so done very quickly, the major training time is simply passing the training examples down the tree. We found that it's possible to reduce the number of trees that are needed in order to get reasonably good performance by, instead of being totally at random, have at each node 5 totally random choices and then assess how well each of them does and choose the one which performs best. And we use the Gini criterion to assess the accuracy of the different alternatives. So this reduces the number of trees and that leads to faster training and also faster classification. And it slightly improves classification performance. So if we now compare this proximity forest, as we call the resulting stochastic ensemble algorithm, our intention was to produce a fast variant of the elastic ensemble. But when we do a comparison across the UCR repository, we can actually see that it is significant. It is more accurate than the elastic ensemble on significantly more tasks. So it is significantly more often more accurate. And indeed, it's statistically indistinguishable from the first version of code, although it doesn't quite reach the level of the second version. So it's not only substantially more accurate than the elastic ensemble, it's also orders of magnitude faster. So the elastic ensemble takes days to process thousands of examples. We can process the million examples from the satellite problem in 17 hours. There are yet more scalable time series classifiers, so BOSS-VS and Weasel. However, the highly scalable one does not achieve as high classification on our satellite classification task. So we can see that proximity forest is not only faster than most of them, but also more accurate. Moving on to the next variant of the tree-based classifier. So this is the PhD work of Ahmed Shafaz. So proximity forest is taking the elastic ensemble component of the highly accurate COAT classifier, but COAT also includes interval-based and dictionary-based components. So we decided to try to introduce those into our tree classifier. So it's using 3 types of splitting function. It's still selecting candidate splits at random. So selecting a large pool of them and then doing a selection using the Gini index. So the similarity-based component is just the proximity forest I've already explained. The dictionary-based splitter recodes the time series using what is called a dictionary-based technique. So essentially what it's doing is it's discretizing the values within the series. And then it takes sub-sequences of a particular length. Here we have a length 3, and it puts the interval, which have been called A, B, C, D, E here, into a, in this case, 3-character word. Then simply for each of those words creates a histogram of its frequency. So it converts a time series looking like this into a histogram of how frequent different local patterns are. The BOSS dictionary-based classifier included in COAT acts in this way. What we do is we, at each node, select a random dictionary transformation, then select a reference histogram per class. So we again choose one of the series to be a reference, to be an exemplar series, and take its histogram, and then we use a histogram similarity measure. So we partition the distance again on proximity, but proximity to the reference histograms in this case. We use random transformations, whereas BOSS chooses the transformations to use using cross-validation. The interval splitter takes the idea that I presented in my ECG example at the very beginning of how different things may be relevant, that sometimes local patterns are important. So what the interval-based splitter does is select a particular region within the time series and then take some simple summary statistics of what is happening within those regions. The 4 summary statistics that are used in the version of this RISE used in the original COAT are the autocorrelation function, the partial autocorrelation function, autoregression, and power spectrum. So we use those, and again we let me, I think we explain it here. So what we're going to do, so in RISE, they very carefully select good intervals. What we're going to do is select random intervals, and we're going to take random transforms. So of the 4 transforms, randomly select one. Then we'll simply use that for a classic decision tree attribute value split. When we add these 2 additional type of splitters, TS-Chief was able to achieve the same level of accuracy as HiveCode. And here I'm showing a scatter diagram. So each of these little boxes is represents one of the University of California Riverside benchmark tasks. We're plotting the accuracy of TS-Chief against the accuracy of HiveCode for each of these tasks. Above this line means TS-Chief has the higher accuracy. Below the line means HiveCode has the higher accuracy. One of the nice things is that there are some tasks for which each is significantly more accurate than the other. And why is this nice? Because it shows that there's still a lot of room for developing more accurate time series classifiers. So TS-Chief is performing at a comparable level to HiveCode, but it is vastly more scalable. So on our on our Earth observation task, we're able to scale up to 130,000 time series and learn from that in 2 days, whereas Hivecoat requires 8 days to learn from just 1,500 series. Okay, so moving on, we next go to our deep learning approach. So deep learning has revolutionized many fields of machine learning, and there's every reason to believe it might be good in time series classification. But early attempts at performing deep learning in time series classification were not achieving the level of performance of a Hivecoat. So we thought that this may be because we're not extracting the correct information. And convolutions which have been developed for use in image recognition tasks appear to be highly applicable to time series. So a convolution is simply a little mask of values. You multiply the values within the mask to a region of the image and then plot that in order to highlight various aspects of the image. Here we're seeing the result of a edge detection convolution applied to this image. We can do the same trick with time series. If we take this simple filter, -1, -1, 0, 1, 1, and run that along a time series, then we get a resulting time series that represents the gradient of the original time series. So these filters can pick out many different aspects of a time series that may be relevant. The Inception Architecture was originally proposed by Google for image recognition tasks. And its idea was to apply convolutions at multiple resolutions in order to capture different types of patterns. Problem then is that so each application of a convolution results in a new image. So you need ways of, so if you apply many convolutions, you're exploding the amount of information you have. So you need ways of bringing that back down. And the way in which that's done is by what's called a bottleneck layer, which brings the result back to a single image-like thing. So we applied this idea to time series instead of images. So you have an input time series. You then apply multiple convolutions at different resolutions, which then gets you effectively a multi-dimensional time series, and then you then do this pulling together process, the bottleneck, feed it through more layers and so on, and then you finally do global average pooling, which is a method of reducing the entire series to discrete values. So that's the details of our architecture. And we found that this is a very effective technique, but it had relatively high variance. So we ended up doing an ensemble of 5 of these. There's high variance because the process of training these is not a convex optimization problem. So it's not possible to find a global optima. So we end up in local optimas, and if we ensemble multiple of these local optima, we get a very good overall result. To To cut a long story short, we get comparable accuracy to Hive code. Oops, back up. And again, the time is much better than Hive code, although it must be said that that is time on GPUs as opposed to time on CPUs. So perhaps the amount of power consumed in order to get the result is slightly more comparable. This now brings us to the final of the techniques I'm going to present, Rocket. And this is the PhD work of Angus Dempster. So what Rocket does is exploit the power of convolutional filters. It does that by generating a large number of them at random, 10,000 by default. But then instead of putting it through a deep learning framework, we simply feed the output of all of those convolutional filters into a simple linear classifier. So when we have many examples, we use logistic regression. When we have a small number of examples, we use ridge regression for two reasons. One, it has very strong regularization, which is important when you have few examples. And also, it's able to learn extremely fast for small sample size. So how does this work? We're going to create a random convolution. So that's going to be a series of values like these. Like these. So -1, -1, -1, -1, -1, 2, 2, 2. And we're going to run that along the series. So multiplying each of these points by the values in the convolution. That gives resulting values, and we simply sum those to get a single value. When we do that, we get a new series, which is the result of all of these convolutional operations. We can then do that at multiple dilations. So if we do it at a dilation of 1, we get local series, we get local effects. If we do it at a larger dilation, we get less local effects. If we do it at sufficiently large dilations, then we start to see global effects. To feed these, right, so each time we apply a convolution, we get a new series. We can't feed a full series into a linear classifier, or we can't readily do that. So instead, we want to extract a summary statistic. The summary statistic that we've managed to discover is what we call proportion of positive values. And that is simply what proportion of the values are positive or above 0. But we first apply a bias term which moves the values up or down. So with a high bias, the proportion of values above 0 is going to be small. With a negative bias, the proportion of values is going to be very high. And I think if we were to start over, we wouldn't call this proportion of positive values. We wouldn't call this bias. Instead, we'd be talking about proportion of values above a threshold. I think the easiest way to think about this is we're going to choose a threshold term, and then we're going to work out how many values in the convolved output are above that threshold. With Rocket, we do many choices all at random. So 10,000 times, we're going to choose a length of the filter, 7, 9, or 11. We're going to choose the weights within that filter from normal distribution, centered on 0. We're going to choose a bias term between -1 and 1. So you can think of that as being the threshold that we're going to measure the number of values above. We choose a random dilation term such that the dilated filter is no longer than the series length. And we choose whether to do padding or not, which means do we start with the left edge of the first application of the filter at the left edge of the series, or do we start with the center of the first application of the series at the left, first application of the convolution at the edge of the series, in which case we need to pad beyond the series with zeros. So it's a choice between whether we get a shorter output than the input or get the same length output. And we randomly do that half the time. Then we're going to use two features, the proportion of positive values and simply the maximum value. So that was the first version. And then we developed a, I think in almost all respects, superior version. So mini rocket stands for minimally random, and then the rocket stands for random, and I forget the rest of the details. So it's the minimally random version. So in mini rocket, we just use length 9. We only use 2 weights, -1 and 2. And I'll talk a bit more about the weights in a second. We choose the bias term from the convolutional output. So we actually apply the convolutions to some of the series in the task and get actual output values instead of this arbitrary choice between -1 and 1, which was sometimes giving us always 0 or always 1 as a response. And we have a fixed schedule of dilations. We still have padding used sometimes and not used other times. We simply alternate between them, and we only use proportion of positive values. So to do this in a pictorial form, we have our input series. We have a set of convolutions of kernels we're going to apply. Applying them is the convolution. We get an output series. We then do pooling. So in the original rocket with max or PPV, that gives us features, which we then feed into a linear classifier. With mini rocket, we've got a set fixed of kernels instead of the random ones. They only have the 2 values, -1 and 2. And then the convolutional process can be highly optimized because we know in advance exactly what we're going to be doing. And we have half as many features because we only use PPV. So comparing PPV to max, PPV is almost always superior. And here we're looking at how various versions of the original rocket scale as you increase the quantity of data. So we can see that it's highly scalable. So this is scalability with respect to accuracy. So the more data we have, going up to 1 million examples, the more accurate we are. This is comparing against TS Chief and proximity forest. So if we have fewer convolutions and hence are faster, we get slightly lesser accuracy than TS Chief or proximity forest. But with the full 10,000 examples, we're more accurate, but we're many orders of magnitude. So this is plotting time as we increase the training set size on a log scale. So we can see we're orders of magnitude more efficient than the previous scalable alternatives. Here's showing a similar results with respect to time series length. So significantly more scalable with respect to series length. Here's scalability of mini rocket versus rocket. Again, with respect to training set size. and so orders of magnitude more efficient. And here we have accuracy on the UCR repository. So the most recent versions of Hivecode are now more accurate than TS Chief, but not statistically significantly more often so than either Mini-Rocket or Rocket. But Mini-Rocket and Rocket are statistically significantly more accurate than most of the previous approaches. But Hivecode requires more than 2 weeks, as does TS Chief, to classify the entire, to learn and classify from the entire benchmark repository. Mini-Rocket requires only 8 minutes, whereas Rocket requires 2 hours. Inception time requires more than 4 days on GPUs, and the others all take, the best one requires 13 hours. So you can see we're more accurate than most of the alternatives and many orders of magnitude more efficient. Now, you should always be cautious when someone like me stands, or in this case appears virtually in front of you and says how much better our approaches are than anybody else's. So I thought I'd give you somebody else's assessment. Rocket wasn't designed for multivariate time series classification, but a trivial extension of it applies it to that case, and a paper, recently published by these people assessed Rocket as both the best ranked in terms of accuracy and by far the fastest for multivariate time series classification. There's much more research to do in this area of research. So we've started looking at additional summary statistics. There's no reason to believe positive proportion of positive values or proportion of values above a threshold is in some way a magical way of extracting the most information out of these convolutions. There's no reason to believe that these filters are the best possible set of filters to use. The Rocket features aren't just suitable for time series classification. We've shown they can actually be used for predicting numeric outcomes as well as for classification, and believe that they ought to be good for clustering and anomaly detection. And there's potential for doing this general architecture with other types of data beyond time series. So I think I've run out of time. So fortunately, I've run out of talk also. So in conclusion, Ensemble Techniques have revolutionized time series classification. TS Chief combines the efficiencies of tree-based divide and conquer with the advantages of stochastic selection and exploits many decades of specialized work in time series prediction. Inception time is a very different approach, which brings the power of deep learning and is currently the state of the art in deep learning applied to time series classification. And then Mini-Rocket leapfrogs all of these approaches and provides state-of-the-art accuracy with many, many orders of magnitude less computation. We believe in reproducible research, and we also like people to use our stuff. So please rush out and download these systems and start using them. And this has been the work of many, many, many people. And these are key members of the team. Thank you. Over to you.
Thank you, Geoff. Was a great talk, actually. I learned something, definitely. So we can start officially the discussion session. If somebody from the audience has questions, please just ask the question. I think you will be heard. This microphone is good.
I have an easy question, I think. So in the first one, when you were doing the red wave and then the green wave, and you were decided then to choose them randomly, but then you chose 5 to see which one was the best, because if you chose a red one for the left and a red one for the right, then it wouldn't have been a very good tree, right? So you chose several and then you picked the one that seemed to work best, right? So
so I perhaps didn't quite explain that in full detail. So we have a branch associated with each class, and then we randomly select one case from each class to be the exemplar for that class. So we always are going to, in this case, have a red one and a green one.
All right. See,
so
yeah.
In the first version of Proximity Forest, we just made that random choice once and randomly chose a distance measure and parameterization, and that was just it. With the second version, we did that random choice 5 times, right? So if there were 10 examples of each class, and that means there'd be 100 possible pairs, and we would be choosing 5 of those 100 possible pairs. Then there's 11 distance measures, and each of them, or most of them, have 100 possible parameterization. So that's 11,000 distance measures. So that would have been over 1 million possibilities for what the choice is, and we choose 5 of those at random and then select the best amongst those 5.
So my question was, in the later systems, did you use the same similar thing when you had to choose something?
Yes, so I skipped over that detail a little bit. With TS Chief, we kept 5 of these similarity-based splitters, and then we had larger numbers of the other splitters for 2 reasons. The other splitters tended to be less powerful, so you needed to do more of them in order to give them a chance of beating the similarity-based ones. And also they're much faster, so you could afford to do more.
Yeah, so you did continue with the thing of trying multiple things and
many stochastic possibilities and selecting the best of a pool.
Yeah, because I would have thought if you just stochastically chose one thing, it would do much less well than if you chose a number of times and then tried to pick the one that seemed to be working.
So my hypothesis is, right, because we continue until we have a pure tree.
Okay.
And my hypothesis is that if you had enough trees, then just doing it at random is actually going to be superior because it's less biased.
All right.
But if you're not going to have 1 million trees, which may be the number you need, then you're going to need to do something a bit cleverer to get the best possible accuracy within the limited number of trees.
All right, that makes sense.
Hi, Geoff.
Hi.
It's Jacek Kowalski from Australian Unity.
Hi.
We collect data from IoT sensors, which we use for monitoring rehabilitation at home for people who had knee or hip replacement operation.
Yes.
And what we found is that multi-layer Lstms, so it's typically like 2 Lstm layers and 1 dense layer, and we classify into 20 classes, and they are doing a reasonably good job.
Mm-hmm.
Actually, I'll be very keen to apply some of the techniques that you guys have come up with. But have you looked at LSTMs? Obviously, they are not very scalable.
So at one stage, LSTMs were considered the most accurate deep learning approach, but the convolutional approaches across the UCR repository, and I think we need to be a little bit cautious here because there's always a worry with the field of research like this, which uses a single benchmark problem or set of problems to compare things, that you may be tuning performance too much just to that. But across the UCR repository, convolutional approaches appear to be much more powerful than LSTMs.
Actually, we tried both, and in our case, obviously, there is a lot of things that you can do with convnets, but we tried a few, but LSTM seemed to be doing a reasonable job, and it was really simple.
Yes. So one of the things is there are just so many things which may be relevant to different time series analysis tasks that it's really foolish to expect one to be best at everything.
Look, if you are looking for data for your PhD students or students in general, I'm more than happy to give you some.
So if it's possible to make it public, then we would be delighted.
Yes, because it is all anonymized, and you won't know, which patient the data belongs to. So yeah, I'm happy to.
Oh, that's wonderful. If you would be prepared to share that with us, then we would be more than happy to share the performance of our algorithms on it.
Okay, so we have to catch up one day and
probably.
Yep.
Okay, there's a question.
I've got a question about Rocket, so you have 10,000 trees is the parameter that was chosen. I saw in one of your graphs you have one for a performance metric for 10 and 100, 10,000. Is 10,000 just the point at which you get like diminishing returns, or why was 10,000 chosen? And have you tried a larger number as well?
So the real reason 10,000 was chosen, where's the relevant graph? The real reason, I haven't got it here. The real reason 10,000 was chosen was because it put on one of these plots Rocket at the same level as Hivecoat, right? Whereas smaller numbers didn't. So we chose the smallest number, which put us to the right of Hivecoat. So in some sense, it's a slightly sneaky choice.
I get that. Just how much closer to the state of the art do you get with, say, 100,000, or you tried?
So it's a real story of diminishing returns. Okay. We don't find any substantial improvement with Rocket above around 10,000 on most tasks. And again, it's one of those things where from task to task it can vary a bit.
Cool. Cheers.
So where from here is your future work really focusing on Rocket only, or are you still considering proximity forest or other approaches?
Good question. So Rocket is certainly the key foundation for just pure black box classification tasks, and we are working on numerous fronts there. But also, it's very important in some contexts to have explainable systems or understandable models, and I think the most promising path towards that is the tree-based classifiers. So we're certainly keen to pursue the tree-based classifiers from that perspective. plus there's been a lot of work on tuning Hive Code, and I think many things that they've done that TS Chief could benefit from. Certainly have not abandoned the tree-based approaches. At this stage, the deep learning doesn't seem to have a strong place because the extra million or so, or the many millions of extra parameters just don't seem to be needed.
In this respect, because you said that you tested this on the big repository of different data sets, did analysis maybe to see which of the filters or which of the splitters performed very well across the different data sets? If you can recommend, not recommend, sorry, like, did you do a more in-depth analysis, seeing, okay, if I choose this splitters at early stage in the tree when I'm developing, then I get much better results, somehow understanding the inside of the workings of your algorithm in a way, with respect to the different types of data sets you had?
Yeah, thank you. It's a interesting area to explore, and indeed we've got one student working on this. So I wouldn't be too keen on working on trying to tune the choice of splitters too much to the UCR repository, because I don't think that the UCR repository reflects the all of useful and interesting time series problems. But I think there is a lot of potential for tuning the splitters on a task-by-task basis. So I think it's entirely likely that for some tasks, say the similarity splitters are going to be most important, whereas for others, the interval ones are. So one of the things that we're looking at is whether it's possible to learn while you're learning what the most useful splitters are and exploit that in some way. So you can consider each time you have a pool of candidates and do a Gini evaluation to select the best one, you can consider each of those as a potential chance for learning. In some way, you're learning that this type of split looks more productive than these ones. So we're looking at how you might learn from that and tune the pools of available splitters as you proceed through the learning task.
When you said different tasks, did you mean, motor sensor versus IoT, or did you mean like classification versus amplitude versus, because you've talked about both things, right?
So what I meant is that for a particular application of classification, so it might be a different type of data, so it might be one type of sensor as opposed to another type of sensor, or it might be, as I showed with the very early slide, with the ECG data, exactly the same data you might use for many different classification tasks. So is the heartbeat regular or irregular? Is it strong or weak?
So that's more what you meant by task.
So that's what I meant by different tasks. And then each of those different tasks, different aspects of the series may be relevant to the task.
Yep.
Yep, makes sense. Is there any question in the audience? Is there any question in the chat? Because I see that's red.
Yeah, no, that's answered.
That's an answer. Okay.
What is the question? Why can't?
I don't think they heard you, Jörg.
No, you have to say it.
Any questions from our guests in Waikato?
Any questions here? Yeah, please go ahead.
Thank you. Maybe I have a quick question. Is for your inception model, and you define a one-dimensional convolution kernel over the time series. And I just wonder, have you tried to stack the time series together to form a two-dimensional matrix, and then you perform two-dimensional convolution? And if we do so, and what is the will there's and benefits for the one-dimensional convolution comparing to the two-dimensional case? Thank you.
Nice question, thank you. There are a number of ways you might consider this. So I think you might have been suggesting taking multiple time series and stacking them. And I'm not sure what the task would be for which that was suitable. But another way in which you can interpret the question is, what if you have a series that actually has multiple variables in it? Right, so you might have multiple sensors on the one device, for example, and so that's multivariate time series classification. And the inception time architecture, let's see if I can find where the diagram is actually directly applicable to that. So I showed the input as being a single dimensional series, but you can see that's then fed into one of these inception layers, and each of those inception layers actually outputs multiple series, so results of different convolutions at different resolutions. So the input to this inception layer could equally be a multi-dimensional series. So our implementation actually accepts multi-dimensional series here. And if there was an application where it made sense to have multiple series instead of a single series, you could also stack multiple series and feed them through. So yes, indeed, that is a both rational thing to do and relatively straightforward thing to do.
Thank you.
And I have a question, please. So you mentioned that for different time series in the in the repository, basically the rankings of different algorithms are different, and also you mentioned that LSTM also does well on some data sets, but does pretty bad on others. So is there any way of like do the rankings show any sort of patterns, like, or like does it seem to be completely random, like or in other words, is there a way of guessing which algorithm would perform on a task before trying the algorithms on the task? Or basically, I mean, does the tasks have a certain sort of semantic meaning that would determine which algorithm will work well on them?
So very good question, and it would be a very, very desirable tool if somebody could develop a technique for predicting what type of algorithm is going to be most applicable to a particular time series analysis task. But I fear that the properties, right? So I'm confident there are properties of the task which determine which approaches are best. But I fear that the relevant properties fall within the function, right? So the true function that maps the series onto the outputs, right? So if you knew what the true function was, then you would be able to extract from that the properties which would enable you to determine what would be the best learner to approximate that function. But of course, if you knew the function, then you wouldn't need to approximate it. So the problem would be gone. So I don't think that it's going to be dominated by the properties of the underlying series. And I think the example I gave of all the different classification tasks you might have for ECGs shows that fairly clearly.
Okay, thank you. So we can do no better than random guess.
Well, what is typically done is a process like leave one out cross-validation. So you try different techniques and see which ones perform better in practice.
Thank you.
Thank you.
By the way, sorry, just one follow-up question, if you don't mind. Thank you very much. Does transfer learning apply to this problem? Like, I mean, if we have presumably two time series problems that are quite similar, then do we benefit from transferring from one time series to another one?
Thank you very much for that question, because it's an area that I'm extremely interested in. And we've done some work on. So the motivating application for much of our work is the Earth observation, and different regions of the Earth differ very greatly in how the way they appear from space relates to the thing that we're interested in being able to determine. So for example, if you're wanting to determine what crop somebody's growing, the varieties of wheat that are grown in different parts of the Earth are actually different to each other. So they're going to appear different from space. The agricultural practices are different. The seasons are different. So the growing cycles are different. You can't just learn a model in one region and then apply it to the entire globe. And this is problematic because the labeled data we have from which we can learn models is quite rich in the developed world and very sparse in the developing world. So much of the world's land area, it's very hard to get the labeled data for, but you can't just learn the models in one region and directly apply them elsewhere. So we are studying transfer learning, and we've shown, for example, that even within France, where a lot of our labeled data comes from, a land use map trained in central France doesn't transfer very well to the southeast, where the climate is quite different.
Thank you.
Thank you. So if there are no questions, okay, there are no questions from the audience and from the online audience, then I will thank the speaker, Geoff, again.
Well, thank you all very much, and I hope that sometime in the not too distant future, I'm able to actually come and speak to you all in person rather than doing it virtually as we have today. But thank you very much for giving me the opportunity to present our work today.
Thank you. Yeah, it was great. Thank you. So we're going to close this session. Thank you all for coming, and we'll see you probably on our next May session. We'll have a, no, sorry, that will be June session, yeah? And in June, we'll have a guest from Netherlands. Do you remember our speaker name? I forgot, Jan. Yeah, okay. So we'll send an announcement. So have a good evening or good afternoon, wherever you are in the globe. So bye.
Thank you.
Thank you.
Thank you.
Bye-bye.